people can listen back to it later. Seen is a postdoc with both myself and with Clay Curtis in the Department of Psychology at NYU. And this work actually stems from a class project, believe it or not, that he started when he was taking my Bayesian inference class many years ago. But then we pursued it afterwards because we thought it was very interesting. So without further ado, Sien, you have the floor.
Hello, everyone. I'm Shane. Nice to see you guys, but actually I cannot see your faces. And this is actually my first public talk, so I hope that things can run smoothly. And I think I will just start. Today, I'm going to talk about confidence. I'll try to talk about 20 to 30 minutes, and then we'll have an open discussion. Okay. So just a brief introduction about what confidence is, because neural processing is inherently noisy. So making a decision always involves uncertainty. And people often have a sense of knowing about that decision and about the quality of the decision they made. And confidence is not only just a subjective feeling, it also influences people's subsequent behavior and how they plan for the future. And this is an example that I like and I use a lot when I talk about confidence. For example, if you are as young as me, I believe that you have seen this Captcha Task before. Basically, the website is trying to probe whether you're a robot or a human. So in this example, if you feel that you're confident about what this word is, what you will do is probably just type in your answer and hit enter button. But if you're unconfident about what this word is, what you might do is that you might click the reload button to ask for a new word, right? So this kind of showed that how confidence influence one's behavior. And it is still an open question about how observers compute and report confidence when they're asked about it. And in the literature, it is often assumed or suggested that when asked about confidence, what observers would do or what they should do is that they would report something that tracks the probability that a decision is correct, meaning confidence should reflect the posterior probability of the chosen category. And we call this Bayesian confidence hypothesis. And I think that you can see this kind of assumption in many studies and literature. So for example, if you just ask observer to categorize grading into two categories, either it's left or right tilt from the vertical line. In both cases here, observer will choose that belongs to the left category. But at the left, observers might report that they have lower confidence because posterior is actually very close to 0.5. And at the right, observers will report higher confidence because the probability of correct is quite high. And if you dive into the literature, you will probably find that almost all the studies that investigate the representation of confidence use two alternative forced choice tasks. Okay. Regardless of whether it's a study on monkey or human, neural recording or psychophysics. So in this project, what we did is that we tried to push one step further. We are interested in confidence reports in multiple alternative decisions. And one motivation is a very easy motivation, is that in our daily life, people often face more complex decisions that involve multiple choices. For example, when you try to identify the traffic lights, or when you try to pick one item from the food menu, right? In addition, I think more importantly, in a decision task with many options, how to relate confidence to posterior probability is more complicated. And it actually gives us an opportunity to distinguish different models of confidence reports. And I hope that I can convince you later. So let's just look at our task first. So in this experiment, we asked observers to do 3 AFC task, 3 categorization task. And I hope that I can share the example of the task. Wait a second, I have a demo that I want to show. Yep, so this is the demo of our task. In every trial, observers were presented with 3 colored clouds. And we explicitly told observers that these 3 colored clouds are from a normal distribution and they have the same standard deviation. And these 3 categories only differ in their mean position. And we asked observers to just imagine this as a bird's eye view of 3 groups of people in a parade, and they're in t-shirt of different color. So the first thing observers should do is that they should click a button to categorize this black target dot into one category. For example, you might think that, oh, this person belongs to the blue group. And the second thing they have to do is to report how confident they are in this decision. And it's a 4-point report. I think that I'm quite confident here, so I'll click this. So we can do another trial. So you can see that the location of this category change across trials and also the position of dot change. So I think that here I'm not that confident. Maybe I'll choose this somewhat confident. Okay, so I think you got the task. Let me share things. Yep. So here we are. So this is basically that we ask observers to do. And how do we model observers' category decision report and confidence report in this task? So this is basically the our framework here. First, we assume that after observers see the stimulus here, observers will take some noisy measurement of the target dot in their brain. So they will take some noisy measurement here, X. And we assume that there is some sensory noise involved, and we just model the sensory noise as a circular Gaussian distribution. And after observers have this noisy measurement, they will try to compute a posterior probability for each of the category. And because we assume a uniform prior here, so posterior probability can be simply computed by this equation. The numerator is the likelihood of the category and divided by this normalization constant. And when computing the likelihood of each category, we assume that observers know exactly where each category are. And that is one of the reasons that we kind of just present the category out there. So they know the mean location of that category, and they know the standard deviation of the category. And this sigma is just the sensory noise that I mentioned. Okay, so we have to think about how to go from the posterior probability to 2 responses, right? One is a category decision. And this is actually the report that we don't care about that much in this task. So we just assume that observers always pick the group with the highest posterior. And what we're interested in is the confidence report. And here we will consider 3 different candidates model. We call them the max model, the difference model, and the entropy model. And to explain the 3 model, I will use this ternary plot because we have 3 categories here. So actually, we can visualize all possible posterior distribution using this ternary plot. For example, at the top corner here, the posterior for the red category is 1 and is 0 for the other 2 categories. And if we're at the center here, it means that the posterior distribution is basically uniform. Okay. So the max model follows Bayesian confidence hypothesis. Observers pick the category with the highest posterior, and then they report their confidence based on the posterior of the chosen category. So that's the maximum value in the posterior distribution. In the difference model, confidence is computed as a difference between the best and the second best option. So if the top 2 options are very close, observers will be less confident. And it is also possible that observers would take the information from the entire posterior distribution. So we come up with the third model we call entropy model, and we assume that confidence is related to the negative entropy of the entire posterior distribution. And you can just think of entropy as a value variance of a distribution, but it can be used for describing a discrete variable like what we have here. So now we have these three models, right? And the color in these colorful triangles represent the mapping between posterior distribution to confidence for each of the model. And we can see that actually the pattern for each models are different. So we can kind of feel kind of confident that we should be able to distinguish these three models, right? But what would happen if we go back to 2 AFC task? What if we only have 2 choices, right? So if we only have 2 options, we can still write the equation for each model, but under the constraint that the 2 posterior value have to sum up to 1. So we can actually just rewrite all the equations. So all the models will eventually just depends on one value, which is the probability of the chosen category. So all the model collapse to one model. So this just simply illustrates that we need more alternatives to distinguish these hypotheses. So before I jump into the results section, I want to mention that in our model, we consider 2 folds of variability. There are 2 sources of variability. The first one is the sensory noise that I just mentioned, modeled as a Gaussian centered around the target dot. The second source of the noise is what we call inference noise or decision noise. And what do I mean by that? So imagine that if we have the same sensory measurement all the time, and if observers can compute posterior probability perfectly, they should just end up with the same posterior distribution all the time, presumably at this pink star here. But here we assume that observers compute the posterior probabilities in an imperfect way. So what they will end up with is that across different trials, the posterior they have access to is something that jitter around the mean, the true posterior. So this is what we call a noisy inference. Okay, and just to elaborate that, what observers have access to is actually this Q, and you can think of Q as a noisy posterior, and they will make decision and report confidence based on the Q. And we model it by using a Dirichlet distribution, and it has a mean at a P. The P is the true posterior. And we also have one free parameter alpha to adjust the magnitude of the inference noise. But just for simplicity, throughout the talk, I will just talk about P. Okay, so when we fit the model to data, we have these 3 parameters. We have 2 noise parameters, 1 sensory noise, 1 inference noise. We also have a lapse rate in all the model. In addition, we have to fit 3 criterion. The reason is that regardless of which model you use, the output of these models are a continuous real value between 0 and 1. But observers made button presses at 4 levels. So we fit 3 parameters to just cut this continuous value to 3 discrete steps. And we use maximum likelihood to fit the data and find the best fit parameters. So you can think of as like in each trial, we try to account for the joint distribution of decision report and confidence report. Because in each trial, observers can choose any one of the 3 categories. They can also report confidence at 4 different levels. And we will compute this distribution for each trial and then compute the likelihood of the model given the entire data set. So in experiment 1, we tested 4 different categories illustrated as here. So all the categories are aligned and they only differed in their mean horizontal locations. and we randomly put the black target dot within a range. And here are the results for the first two conditions. At the top here, these are just illustration of the distribution of the three categories. And here, the black curve represent the data. So you can see that it kind of makes sense. The x-axis represent the target dot location. When the target is very far away from the center of the screen, observer have higher confidence, and then it kind of drop. And when the target dot move into the center, the confidence kind of bump up again, and it's more visible for this condition in which the three categories are further apart. And you can already see that the entropy model did not fit the data well. You can see the blue curve here at the bottom row. And an intuitive way to think of this is like, for example, if your target dot is at the center, you will have a posterior distribution that is really flat, right? So entropy model basically just predict that you will have the lowest confidence there, but we did not observe that. And we can look at the other two conditions in which the central category is closer to one or the other. Again, we see that when the target dot was presented at far out category, observers are very confident. And then confidence was very low at the location where the two categories overlap. And it seems like that, you can already see that it seems like that the difference model kind of fit the data better. So there's a question on how similar are fitted criteria parameters across different, for different model. Okay, so the question in the chat is that how the best fit criterion differ across different model, if I understand your question correctly. But because the output of these three models are quite different, right? The difference model, the output is a subtraction of two posterior. The max model is the maximum value, and entropy is the entropy. So I think it's hard to compare the absolute value of those criterion. Yeah. I hope that answers your question. And here, just to illustrate that our model also fit the category decision data. So here, the solid line represents the data. For example, if you follow this solid red line, it represents the probability that observers categorize the target dot into the red group if the target dot location is here. So it kind of makes sense, right? And you can see that the categorization across two category kind of intersect at this vertical line here. And we use AIC to compare the three model, and we found that the difference model has the lowest AIC score. The y-axis that I plotted here is the AIC of the model minus the AIC of the difference model. And we summed that across participants. The error bars are obtained by bootstrapping. Oops. So actually, we did not just fit the three model. We also consider other models. For example, the three bars here are the same three bars here. And what happened to the three bars in the middle here is that we removed the sensory noise from the model, and we only kept the decision noise in the model. And you can see the order of the models are still the same. And it seems that removing the sensory noise did not strongly affect the AIC score. And at the right here, we have three bars. In this model, we removed the inference noise from the model, and we only preserved the sensory noise in the model. And you can see that we still have the same model order, but AIC score is much higher. Mike has a question. Can one consider the difference model as a version of heuristic? Yeah. I think we can discuss that in the discussion. Yeah, I actually have a slide, I have a note about that question, Mike. Okay, so this is a new figure. It looks very similar to the figure. Okay, so this is when we only fit the confidence data without trying to fit the decision data, but basically the results are the same. Okay, so in experiment 1, we test these 4 conditions. And in experiment 2, we test 4 more configurations in which we allow the 3 categories to move both horizontally and vertically. And I can explain why, what is the motivation to do that. So imagine if we are in experiment 1 and the categories are always aligned like this. And if we just don't think about sensory noise and don't think about sensory noise at all, you can simply compute the posterior of each category, right? If you move a target dot from the far left to the far right. If you just do that, actually it's equivalent to moving your posterior like along this curve on this ternary space, right? So you can actually see that if we just test these conditions, we are exploring a very restricted region in the space of posterior distribution. So that is a main motivation that we want to run more conditions. For example, if we have a condition like this, there are 3 categories and they are equal distance to each other. And we can randomly position our target dot in a 2-dimensional fashion, then we can explore a larger range in this space. For example, here we can test a condition in which the target dot had the same distance to all the 3 groups, and it can never happen in experiment 1. So here are the data. Now we illustrate confidence report in a 2-dimensional manner. The X and Y axis here represent the location of the target along the 2-dimension, and the color represent the average confidence rating for each location. And you can kind of see, like in this condition, when the target dot is very close to one category, observer report higher confidence. And observers are not confident when the target dot was at the center. And confidence is overall lower if the 3 categories are very close to each other. And in these 2 conditions, again, one of the category is closer to the other. And basically observers are very confident when the target dot was presented to the group that is standing out alone. And we found extended low confidence locations here when the 2 categories overlap. And these are model fit. You can look at this image forever, but kind of that, for example, entropy model again predicted a contour that looks really different from our real data. And it seems like only the difference model would predict this large extended low confidence region in the 3rd and the 4th column here. And here, again, we use AIC score to compare the model, and we found results that was consistent with experiment 1. So we actually run an additional experiment because in experiment 1 and 2, we did not provide feedback to the observers, so observers did not really know whether they're correct in that particular trial. So here in experiment 3, we're provided feedback, and we sampling the stimuli directly from the true stimulus distribution. But that would also mean that we will have a lot of target dot that's at the far left or far right. Yeah, and these are results. You can see that still we found difference model to be the best model. Yep. Yeah, so here I provide a list about the things that you might be interested in. And I think, for example, we perform a model recovery to make sure that this experiment can really distinguish 3 models. And we also perform model comparison using a BIC score. And we fit either confidence data alone, or we fit category decisions alone. When we fit category decision alone, we compare the effect of different type of noises. Okay. And in addition to the 9 models that I just presented, we actually presented 21 additional models. It included models that consider different type of variabilities. And we also have heuristic model in which the observers did not compute posterior probabilities at all. In heuristic model, observer basically report decision based on some parameters of the stimuli and the sensory measurement they have. And the last question is related to Mike's question in the chat. So Mike was asking whether we can think of the difference model as a heuristic, in which observers basically throw away the least, like the worst category, and then compute posterior or just make their decision based on the top two. I think this is equivalent to the racial model that we had in the paper. So we also speculated about that. So we basically fit a model in which we assume that confidence depends on the likelihood ratio of the top two categories. And the short answer is that we are not able to distinguish difference model and the racial model based on our data in experiment 1 and experiment 2. When we fit it to experiment 3, I think the difference model outperformed the racial model, but just by a little bit. And I think that to really distinguish these models, probably we need more categories, more than 3. The other thing that one might also consider doing might be testing the confidence rating across different number of categories, but that might involve some weird issue. I hope that answered your question. So just to sum up, we found that the difference model outperforms the max and the entropy model. And so our conclusion is that the posteriors of the unchosen options matters. And we should probably rethink the Bayesian confidence hypothesis, especially if observers encounter a more complicated task, meaning more complicated than a simple 2AFC task. Oops. So yeah, that's all I want to say, and thank you very much for listening, and it's time to discuss. And I think that Adobe already asked a question on Twitter. He was saying, do we really consider this task as a perceptual decision task? He thinks that it can be more cognitive. And it is true that he mentioned that this can be a little bit semantic, and I also feel that it can be a little bit semantic. I remember that when I discussed this with Weiji, we often think about this might be a task that is on the borderline of perception and cognition, and but if you really think about it, it's actually just a location categorization task, right? You try to categorize the target dots based on the location. And if you replace the location as like orientation categorization task, you might think that is more perception-y. Yep. Weiji, do you have anything to say about this?
Yeah, I find this a very difficult distinction to make. And I know that philosophers actually have tried, and it's a hard problem. It's also not that important because very often we propose similar processes for perceptual and cognitive processes. So I'm personally, I don't lie awake about where exactly the borderline between perception and cognition lies.
Okay, so I think people can also, there are some questions in the chat, and I think people can also ask questions by raising their hands if they want to talk.
Yeah, so there are two new questions from Goki and Pascal.
Oh, can we let, because Dobie said that he can explain it a little bit. Where's Dobie? Yeah. Dobie. Can you speak, Dobie?
Can you hear me now?
Yep. Yep.
Okay, wonderful. Yeah, so the motivation for this question, I think in perception we have one big difficulty, which is we know exactly what we present as experimenters, but we do not know exactly how this is encoded in the brain. So you can present your 3 categories, but how those 3 categories encoded, there's actually a bunch of different possibilities. And I think that's where perception is difficult. And I think the way I think about your task is more of a cognitive task, because in your task you don't have the problem of like modeling what people are encoding, because the stimuli are in front of them for a long time. They can compute each of the three likelihoods, and then they can pick how to make the confidence judgment. But if the stimuli were presented very fast, in a perceptual decision-making kind of design, then it's not obvious how the information is encoded. And I think if, for example, you present it very fast, and there's noise, like more sensory noise and all of that, it could be that the results are different because the encoding is different. This is not a criticism. This is just an opinion that this may be, things may be different if you present stimuli very fast and if you present stimuli that are noisier.
Got it.
Do you want to go to Goki's question? So in the chat.
Yep. So Goki said, I'm curious about the difference of results between 1 and 3 in the leftmost column of experiment 3. I don't see, while I see a peak in experiment 1. Let me share the screen. Yeah, I think what Goki was asking about is that this bump at the middle is not that obvious in experiment 1. I don't really have a good explanation for that. But one thing that is consistent, I think, with experiment 1 is that the bump is always more obvious for the second configuration, where the 3 categories are further apart. And this bump is weaker, or is hard to see here, but you can see in experiment 1, it is also the case that the bump is smaller in the first condition. So I think the trend is the same. So you can imagine, as long if this is already a weak effect, if those observers have say noisy perception or categorization performance, yeah, it might go away. So I think that is a problem about try to map out something that's already weak there. Yep. Pascal's question, when the best 2 distributions overlap, the second best is as good as the first best by definition. So the difference should be 0. So how can there be a difference in human confidence reports and model between the first 2 configuration and through for the second ones to be higher than the first one? I think you are talking about the data for figure 3. Let me try to move there. Sorry, I cannot see the question that way. How can there be a difference in human confidence reports and model between the first 2 configurations in figure 3? The trough for the second one seems to be a bit higher than the first one. Weiji, can you decipher that question?
Yes, I think my best attempt is that it's actually about that same figure. So we're talking about the first 2 panels in A, right? So these are the 2 different conditions.
Yep.
And we're talking about the same, about the troughs here. So the trough in panel in the first column and in the second column. Pascal, is that indeed what we're asking about here? Okay. In the model, they actually look very similar to me.
Yep.
They should, as you said. There is a little bit of a difference here between the left trough and the right trough in panel B, but the model is not able to account for that.
Yeah.
So I think that might be some idiosyncratic source of asymmetry. Idiosyncratic sort of asymmetry.
Yeah. Just to add up one more points here, it is true that when the two categories overlap, like these two dip, they should all be at the same level, right? If you just think about exactly those 4 points. But when we visualize the data and also when we try to visualize the model, we smooth it. So you can imagine in the first condition, the trough is actually very like smooth. And in the second column, maybe it goes really deep, but it's very sharp. So if you have a little bit bending or smoothing, then that points would go up a little bit. That also contribute to the thing that you saw there. Yeah.
Rosanna is also asking about this figure, so you might as well address that. The red and blue sum to green in the center of the space. No, these are. You can already see that here that's not true, right? The sum and the red and the blue are together lower than the green. Okay, shall we go up to the next question? Crejo.
Okay.
And I'm going to stop sharing. Yeah.
Okay. The question is do your results speak to the paradoxes that arise when the number of choices is increased from 2 to 3? I think that our results do not speak to the question about, say, if you run a 2A FC trial and 3 FC trial and try to X-observe to compare the confidence across those two trials. I think we did not investigate that, or our results did not really speak to that.
But yeah, I think you said that in the 2FC, all these models would have amounted to the same.
Oh yeah, yeah.
It was necessary to go to at least 3 choices in order to distinguish these models.
Right.
You want to go to the next one?
Yeah. Is there some estimate of how many categories becomes too many for someone to fit these models? And how do you think the difference model will work when you have 2 or more equally distant best choices? I think this is a good question. I feel that if we stay with the same number of category, for example, if we run the, say, 4 AFC or 5 AFC tasks, but just test one number, for example, we run a 5 AFC experiments, the model, I would guess that it would still work. What I can think of a weird scenario is that if you have a 5 AFC trial and a 4 AFC trial, and you try to compare the results across that two, you might imagine that if the target is equal distance to all the 5 categories in one trial, and the other trial is equal distance to maybe all 4 categories, they might rate the 4AFC task to be more confident. So this discrepancy, you can kind of find that out for this model if you try to compare a different number of categories and directly compare them. Yeah, that's a good point.
And that, I think, also covers Yuval's question about how about more than 3 categories.
Yeah.
Pascal also suggests a model where the participant would take a small neighborhood around the black dot and compute a fraction of red, green, and blue dots within that neighborhood. I don't remember that as one of the heuristic models, was it?
Yeah, so we fitted a few heuristic model. There are actually 3, I think. But we did not do exactly what Pascal, you mentioned here, to look at the dot neighboring the target. One of our heuristic model is compute the target dots to the distance to the 3 category mean. So we have 3 distance value. and do some computation like difference or weighted sum of those 3 distance value. The other heuristic model related to this we tested is that we assume that observers, based on the 3 color clouds, they can draw the boundary perfectly between each of the 2 categories, and observers compute the target dot to those boundaries and use that for confidence report. So those are the 2 heuristics model that we fit. We did not fit this one that you mentioned. And is there a particular assumption that you make for fitting the modeling using maximum likelihood approach? Weiji, what do you think there?
So it is a pretty standard fitting process. I don't remember any great difficulties in fitting these models. The expressions for likelihoods are analytic. So that's right, I see. They're analytical. You don't have to simulate them. Or in the presence of measurements noise, you do have to simulate, I think.
Yeah, we use simulation to fit our model to simulate the distribution of the responses.
Okay, I stand corrected. So there is simulation needed. So that is a bit of a complication. Yeah, the methods that we use in the lab, they can deal with that. So often we use Bayesian adaptive direct search, which is designed to fit models that have stochastic likelihood functions. Anything else you wanted to say about that, Sien?
I think that's all I can say too. So Sean Jen, I think that's Jen. Do you have any ideas on how to compute the accuracy of confidence or metacognitive sensitivity in the theory FC paradigm? I personally did not. I'm not super familiar with the metacognitive sensitivity literatures, like their meta D prime or things like that. Yeah, you can definitely ask Dobie Rockney this question and talk to him.
Turning us back to another attendant.
Yeah, so Sean, please send your question to Dobie.
Like as far as I know, meta D prime fits naturally in a 2AFC, and just like all of signal detection theory is really formulated in terms of 2AFC. As soon as you go to NAFC, it becomes really, really messy. And often people do things like pairwise comparisons, but at some point I got lost trying to learn that. So I'm not sure either.
Yeah. So Dobie posted another question saying, could it be that there's a 4th model that's better than all existing ones? Does the difference model make any counterintuitive predictions so we can confirm them? Wouldn't that give us even more certainty that the difference model is indeed a good description of what subjects are doing? Yeah, I think this is related to actually some ongoing projects in the lab. I think that we are not like 100% satisfied with the difference model. I think as Weiji would say that he still thinks that it's like a post hoc model. Oh, is that the word that you use, Weiji?
An ad hoc model, maybe.
Oh, ad hoc model, yeah. So for example, the question that Mike asked earlier, is it possible that we can kind of think of it as observer reducing 3 options to 2 options? That's kind of one way to think about it. And in our discussion, actually, we talk about this interpretation about the ratio model. And we also talk about the other interpretation in which maybe observers will try to use the noisy posterior they have to infer back the true posterior. And that will kind of give you another model and can really have a more conceptually satisfying interpretation. And those are the things that we are trying to test now. And
I just wanted to elaborate a little bit on that, because to me, that is actually one of the most exciting directions. Also one that another student in the lab is working on right now. It's the idea that if you have 2 options that have the same posterior probability, let's say 40, 40, 20, right? So the top 2 choices are the same posterior probability. then you would be very unconfident according to the difference model, because that difference is 0. And you can, of course, have a graded version of that, where, like, if you have a small difference, it's just minimally confident. Now, why could you be minimally confident if you have, let's say, a difference between 40% and 38%? Well, what if the question that you're really trying to answer is whether the option that you chose actually is the one with the highest posterior probability, right? So you would be second guessing yourself and you say, was this the best option I could have chosen, regardless of its probability, right? So if that's your source of confidence or unconfidence, then that would actually map onto something very similar to the difference model. If you make the additional assumption that observers don't have access to the exact posteriors, but only to noisy versions of them, right? So if you are measuring posteriors of 40% and 38%, what if you, in reality, it could have been 39% and 42% respectively, right? So in which case the option that you chose actually does not have the highest posterior. So then it becomes a signal detection theory problem in the space of posterior probabilities, where the confidence is related to the signal to noise ratio. So the difference in the true posteriors over the amount of noise in those representations of posteriors. So this would be a model where the observer would be trying to infer what an ideal observer would be believing about the stimuli based on noisy internal representations of those posteriors. So it becomes a signal detection theory problem in the space of posteriors. And from our initial explorations, that seems to be giving something that's very close to the diff model, but we're not ready yet to have a full story, but we do mention that in the discussion of this paper.
Okay, Benjamin Peters asks, how could we think about how the difference model can be implemented computationally? Would this scale well to a lot of categories? And a related question, would a normalization model produce similar results? I think we already talked about like the problem or the feasibility about scaling to more alternatives. How do we implement this, say, computationally? I think when I tried to write up the discussion about this, I think I did check many literatures, mostly from the drift distribution model camp of people. And sometimes they also have like a neural realistic computational model with with many units and wiring mutual inhibition between them. But I think that the problem might not be that there's no models to model that. It's that there are too many degree of freedoms in how you wire those mutual inhibition between the neural units that are competing. So I believe that they can definitely generate these results because there are lots of degree of freedom there. And regarding whether the results fit well with a normalization model, I think, again, the issue can be the same because there are actually some flexibility in the normalization model. For example, in the, say, Heuristic normalization equation, there's usually an exponent parameters that you can fit that will kind of determine how much normalization you will give to this neuron, whether it's more, say, winner take all or not winner take all. And I believe that there's definitely a parameter regime that can generate this results. But that's just a speculation.
Also, you need to think first about the linking hypothesis from probabilities to neuroactivity. Because if you do that in the most literal sense, that you say there are units that represent probabilities and you would apply normalization to those, then of course you just get normalized probabilities, which is the regular Bayesian model. So you would either have to have a non-traditional normalization like Sine is asking, is suggesting, or you would have to have a linking hypothesis where activity is not directly proportional to probability.
Yeah, I think the issue which you mentioned can be an even more daunting issue, like how you link the neural response you model to the probability that we conceptualize here. Right? Christian, Knife comments regarding the calculation class and confidence. The method reminded me a little bit fuzzy logic, specifically the function fuzzy k-means, where you have continuous function too. It works to try these approaches, or it could work this problem. Yeah, I think this problem about like the fuzzy k-means or the k-means, if I understand this correctly, it's kind of related to the heuristic model that Pascal mentioned earlier about looking at the dots neighboring the target. Yeah. Don't have much to say on that, if I understand your question correctly. Dobie said, follow up on Weiji's response. You may have trials that are close to 50-50-0 and other trial 40-40-20. But this no difference in mean confidence between the two. Can you test if this is true?
I would say we are essentially doing that, right?
Yeah,
that's how the project started, but instead of handpicking those situations, we let them emerge naturally from a generative model. But yeah, at those intersection points, when the third category is very far away, then you essentially have a 50-50 situation. And then if the third category is closer, then you would have more of a 40-40-20 type of situation. Yeah. Did we compare those specific points? I don't believe so. Yeah. But yeah, it's usual story that you get more power out of your data if you just fit all of them simultaneously with a model. It might be interesting to highlight some of the special situations. Like these ones, though.
Yeah. Lucy, it could be interesting to see if the difference model could predict whether observers, subjects would be more likely to change their mind after making a decision and reporting confidence, like measuring regret too. Yeah, I really like this idea about having a task that's not just asking observers to report something subjectively, but designing a task to show that internal variable that we call confidence can influence their subsequent behavior or the task at hand. Yeah, I think that's definitely a great future direction.
Yeah, absolutely. Like one thing that people say about confidence is that it's a signal for whether you have to gather more information or whether you want to continue learning. But would it then be the confidence that we're asking people to report, so this explicit confidence, or would it be the underlying posterior that would drive that subsequent learning or decision making? Great question. Yeah.
I think we cover all the questions and time's up. Yep.
Thank you all very much for attending. If you have more questions, please don't hesitate to contact us. Our email addresses can be easily found. The recording of this will be made available on our lab website. And we hope to see you in a subsequent virtual journal club. Take care and stay safe.
Thank you.